Alright, so first we want to recall the elementary row operations. Recall the elementary row operations. There are three of them. You can multiply a row by a constant, as long as it's not zero. Two, you can swap the order of two rows, so you can interchange them. And the third operation is you can add. You can add one row or a multiple of one row to another. Okay, and so these are the elementary row operations, which we use for putting something in like row echelon form or reduced row echelon form, and so on and so forth. So that's just to remind us. So these are the elementary row operations, and the topic for today are what are called elementary matrices, and they're called elementary because they come from these elementary row operations. So here's a definition. So an elementary matrix So an elementary matrix is a matrix that is obtained by applying a single elementary row operation to an identity matrix. Okay, so these are what the elementary matrices look like. Or that's what they are, sorry. So just a couple of examples. So we can take the matrix 1, 0, 0, like, say 3. That's an example of an elementary, so this is elementary. And how can you do that? Or how can you see that it's elementary? What you can do is you can scale the bottom row of the identity matrix. So typically you just like say this matrix is an elementary matrix, but if you want to see, so why is it, so to see why it is elementary, is what you can do is you can take this 2 by 2 identity matrix, and then you can basically do 3 times the second row, and you get this matrix. So indeed, this matrix here is elementary. Oops. So another example would be, well, the identity matrix is sort of trivially. Here's another example. Say 1, 0, 2, 0, 1, 0, 0, 0, 1 is elementary. And again, we can see that it's elementary. So to see that it's elementary, we can now take the 3 by 3 identity matrix, and we're going to just do a single elementary row operation. Here we're going to do the first row plus twice the third row. So if we do that, we're leaving the last 2 rows alone, and we're doing row 1 plus 2 times row 3, so that gives us 1 plus 2 times 0 is still 1, 0 plus 2 times 0 is still 0, and 0 plus 2 times 1 gives us the 2. So indeed, this is an elementary matrix. And I'm just going to write down a couple others, but I'm not going to continue showing why they're elementary. So you can basically interchange any of the rows. So maybe what you could do is you could take, if you wanted to like swap, like take a 4x4 matrix, then you could swap the like second and say fourth row. So you get something like this. This is also elementary. So this is also elementary. And I just told you where it comes from, because I just took the identity matrix and I just swapped these two rows. So again, swapping. So these are 3 examples, and each one corresponds to a different one of these elementary row operation. Yeah. So this example here comes from scaling a row by a constant. This one here comes from adding a multiple of one row to another row, and this example here comes from swapping rows. Okay, and so why do we care about these elementary matrices? And one reason we care about elementary matrices is the following theorem, which won't prove, but I'll just state for you. So if E is an elementary matrix, which is obtained by performing a certain row operation, so let's just fix a dimension. So E is an elementary matrix, so let's say it's so notice that since elementary matrices are obtained by performing elementary operations on the identity, elementary matrices have to be square, because the identity matrix is square. So let's say E is, say, n by n, elementary matrix obtained by performing a SO operation. Then if M is any, say, n by m matrix, the product E times m, so this is the matrix multiplication. We're allowed to multiply because E is square n times n, and m is n times m. So these two, n. So we're allowed to, they're compatible, so you can multiply them. Then the product matrix is the matrix that results, no, let me not say it like that, is the matrix obtained by applying the certain row operation to m. So there's this cool correspondence. So by definition, E is elementary, so it comes from a certain elementary row operation. And then multiplication by E is the same thing as just performing that row operation. So the same row operation applied to M. So this sort of allows us to give an interpretation of multiplication. Matrix multiplication is very strange. But that's just how it goes. So this is an important theorem. It's important for being able to calculate the inverse of a square matrix. Sorry about that. So here's an example. So say M is the matrix 1, 2, 1, 0, minus 1, 4, 2, 3, 4, and 3, 6, 0. So this is the matrix M. This is obviously not an elementary matrix. And let's consider the elementary matrix E is the matrix, say, 1, 0, 0, 0, 1, 0, 3, 0, 1. So first, let's just observe that E is indeed elementary. Note E is elementary. E corresponds to this certain row operation. The operation is you modify the third row by replacing it by row 3 plus 3R1. And we can check that because how do we get E? We take the 3 by 3 identity matrix, and then if we do this process, so we're just going to modify the third row only, so we're leaving the first two rows alone, and then we're adding 3 times the first row to the second row. So 3 times the first row becomes 3, 0, 0, and then we add it to 0, 0, 1, and we get 3, 0, 1. Okay, so the point is you want to start identifying elementary matrices with elementary row operations. Okay, and so we identify this particular E with that row operation, and under this identification, the row operation, so here we have an actual row operation, and of course here this is just a matrix, but we can reproduce the same row operation by doing matrix multiplication. So in other words, in order to apply this row operation to any matrix, for example, matrix M, we can simply multiply the matrix M by the matrix E. So let's just do that. So let's calculate E times M, and we'll see that this is the same thing as just modifying the third row. As described. Okay, so now we're just going to do matrix multiplication, and you can just, work it out yourself, and you'll see what you get. You get 1, 2, and then you get 4, and I'll do the next column, then you get 0, minus 1, 4 also. Do the next row, you get 2 times 1 gives you 2, then you get 2 times 0, 3 times 1, 3, and then you get 2 times 3 plus 4 gives you 10. And for the last column, you get 3 times 1 gives you 3, 6 times 1 gives you 6, then you get 3 times 3 plus 1 times 0, which is just 9. So that's what you get, and of course, similarly, we'll see that we get the same thing if we just take matrix M, and if we apply the row operation. So if we take the matrix M, and let's do this operation, let's do the row 3 plus 3 times row 1, so we're leaving the first row alone, we're leaving the second row alone, and already you can see that this matrix here so far is the same as the matrix there. And now we're doing row 3 plus 3 row 1, so you're doing 1 plus 3 times 1 gives you 4. You're doing 4 times 3 times 0 is still 4. Doing 4 plus 3 times 2, that's 4 plus 6 is 10. And you're doing 0 plus 3 times 3 is 9. So these, of course, are the same. So that is what this theorem is saying. This theorem is saying that elementary matrices sort of represent performing an elementary row operation. So if you multiply by an elementary matrix, it has to go on the left side. So here you put the elementary matrix on the left side. So M times the elementary matrix is the same thing as just applying the elementary row operation used to define the elementary matrix in the first place. So that's what this theorem is saying.